The general equation of a sine wave with a phase angle of plus and minus phi is given as this. Plus and minus phi is the phase angle of the sine wave. The phase angle of a sinusoidal wave specifies the position of the wave relative to a reference. In this module, 0 degree is taken as the reference point. Here. If phi is equal to 0, v theta is simply a sine wave. In this figure, 4 points are highlighted: the positive peak, the negative peak, and the 2 zero crossing points. These two are zero crossing points because at 0 degree and 180 degrees, the magnitudes are equal to 0. When we draw a waveform, we draw it from left to right. At 0 degree, the waveform is crossing 0 and becoming positive in value. That's why this point is called positive going zero crossing point. When the waveform reaches 180 degrees, the waveform is crossing 0 and become negative in value. Therefore, this point is described as a negative going zero crossing point. As just discussed, this is the general equation of a sine wave with a phase angle. The curve on top shows a sine wave with a positive phase angle. It is because its voltage rises above 0 level earlier than 0 degree. While the lower curve shows a sine wave with a negative phase, it is because its voltage rises above 0 level later than 0 degree. Note that the phase plus and minus phi is not the theta value at here or at here. Let's say phi is 30 degrees. Then for the upper curve, the phase is plus 30 degrees. And for the lower curve, the phase is minus 30 degrees. As A rises above 0 level earlier than B 90 degrees, we say A leads B by 90 degrees or B lags A by 90 degrees. Besides 90 degrees, the phase lead or phase lag can be any value between negative 180 to 180 degrees. It all depends on the positions of the waveforms. If two sinusoidal waveforms have the same phase angle, we say that they are in phase. If the phase difference between the two sinusoidal waveforms is 180 degrees, we say that they are out of phase. This is the mathematical definition of the average value of a periodic waveform. Even without any calculation, the average value of this sinusoidal waveform is obviously equal to 0. It is because its magnitude changes symmetrically above and below the 0 level. The average value over a positive half cycle of a sinusoidal waveform is given as this: 2 over pi times the peak value. This formula is derived from the definition of the average value of a periodic waveform. However, the detail of the derivation will not be provided in this module. The average value of a negative half cycle of a sinusoidal waveform is given as negative 2 divided by pi times the peak value. The root mean square value of a periodic waveform is given as this. From here, we can derive the root mean square value of a sinusoidal waveform as the peak value divided by square root 2, which is approximately equal to 0.707 times the peak value. You may be wondering why we talk about root mean square value. It is because root mean square value is related to power dissipation. Let's explain it with an imaginary experiment. An AC voltage of 50 volt root mean square value is applied to a resistor. The temperature generated from the resistor is recorded to indicate how much power is dissipated from the resistor. Now we replace the AC voltage source with a DC supply. We vary the DC supply voltage until the same temperature is reached. We'll find that the AC root mean square voltage and the DC voltage are the same, equal to 50 volts. This means that a sinusoidal waveform of a certain root mean square voltage produces the same amount of power as a DC waveform of the same voltage. In this video, you have learned the parameters which describes a sinusoidal waveform. These parameters are the peak voltage, the peak-to-peak voltage, the root mean square voltage, frequency, period, and the phase. You have learned the general equation of sine waves to convert radian to degree and degree to radian. And you have learned what phase and phase difference are. For sinusoidal waveform, the FH value is 0. The root mean square voltage is equal to 0.707 of the peak voltage. Next, coming up is Part C, AC circuit analysis.